In this video, we'll continue our discussion of computing the Laplace transform of a power. So here I have Laplace of t to the n, and we've proved that this is equal to n over s times the Laplace of 1 degree lower. And here n is some positive whole number exponent like 1, 2, 3, etc. So let's illustrate the use of this formula. Let's take the Laplace of, say, t to the fourth. N is equal to 4, and so I'm going to apply the formula. I'll have 4 over s times the Laplace of t cubed. I can then keep the 4 over s, my current coefficient, and I'm going to apply the formula again now with n equal to 3. So I'll get 3 over s times the Laplace of 1 degree lower, so now the Laplace of t squared. And I just keep applying it over and over, so I have 4 over s, 3 over s. I'm going to have now times 2 over s times the Laplace of t, which is t to the first. And then 4 over s, 2 over s, 3 over s. I'm going to have a factor of 1 over s now, and it's going to become the Laplace of t to the 0. So we have 4 times 3 times 2 times 1. I have a bunch of s's in the denominator, s to the fourth multiplied together, s to the fourth. And then t to the 0 is 1, so I really need the Laplace of 1, which we've computed, and that's another 1 over s. So in the numerator, I'm going to have a bunch of numbers multiplied together, these consecutive numbers multiplied together. This is a factorial here. 4 times 3 times 2 times 1 is 4 factorial, which we write 4 with an exclamation point there, just as shorthand. And then notice how I get one extra factor of s. It's going to be s to the fifth here. That one extra factor of s came from looking at the Laplace of 1, that degree 0 term. So we're going to need to use factorials in our final result here. And just to review here, 5 factorial simply means to take 5 times 4 times 3 times 2 times 1. Calculate that number. You get, in this case, I think it's 120. And that works for any positive whole number, 1, 2, 3, 4, etc. It doesn't really make sense for 0. What is 0 factorial? How do you take nothing? And it's unclear what it should be based on what we're doing above. It just doesn't seem to apply. But it turns out that the right thing to define 0 factorial to be is 1. It doesn't really match the pattern of what we saw with 4 factorial or 5 factorial, but we're going to define it to be 1 by definition. And it turns out just to be a really good idea to do that. So I think here's our summary here for integer powers, 1, 2, 3, etc. If I take the Laplace of t to the n, I think what we're seeing in this result here is I should see, well, it was t to the fourth, so it should be n factorial over s to the 1 degree higher than what you started with. So t to the fourth, s to the fifth, t to the n, s to the n plus 1 now. There are some special cases here that we could consider. If n is equal to 1, it will be 1 factorial, that's 1. And it's going to be 1 degree higher, so s squared in the denominator. We've already seen that the Laplace of t is 1 over s squared. And in fact, the formula is totally consistent even with this t to the 0 case, the Laplace of 1. If we just follow the formula naively, it should be 0 factorial over, well, it's power 0, so it should be 1 more than that, so it should be s to the first. And we've defined 0 factorial to be 1, so this is 1 over s. Let's look at a quick example. Here I'm going to take the Laplace of 1 plus t cubed, and then I'm taking that entire quantity and squaring it. If I want to apply the Laplace, the first thing I'm going to need to do is expand out all that polynomial to get a bunch of powers of t, and then I'll be able to use linearity. So expand first before taking Laplace. It's going to be 1. There'll be 2 t cubed terms, and then the t cubes multiplied together will give me the t to the 6th for the last term. And then we'll have Laplace of 1 plus 2 times the Laplace of t cubed plus Laplace of t to the 6th. And now we can start applying our formulas. Laplace of 1 is 1 over s. Laplace of t cubed, well, I'll have a 2, and there will be 3 factorial over s to the 1 higher power, s to the 4th. And then here I'll have 6 factorial over s to the 1 higher power, so s to the 7th. You can clean up the coefficients now and simplify the expression if you prefer. 1 over s. 3 factorial is 6, so this will be 12. And 6 factorial turns out to be 720. That's 6 times 5 times 4 times 3 times 2 times 1, 720.